Hello and welcome, friends. It definitely helps to unmute the stream. So, today is going to be day one. Hello and welcome, friends. It definitely helps to unmute the stream. There we go. So today is going to be day one of the Electronics Learning Lab. This is a package that was released by RadioShack sometime 20, 30 years ago. Um, it includes two workbooks, a beginning workbook and an advanced workbook. We'll be going through each of these workbooks over time. The initial bits is this is the Electronics Learning Lab 28-280. It cost me about 55 bucks on eBay. You can find them on eBay, just other shops. They don't make them anymore, unfortunately, and I also don't know if they make anything similar to this today. I can say that Radio Shack has uh, other models based on similar makings to this, but this one was the one that was recommended to me for learning electronics. Um, I'm not really sure what I'm getting into here. It seems like fun. It seems like something that I should know today. We should maybe know all together. Technology itself and electronics definitely rule our lives in every facet um, that is unimaginable. Um, so I'd like to take it all the way back to the basics. See what we've got here. All right. So to start, we're gonna unbox. I got a little bit of a tear here. That's how it came. No big deal. It is what it is, right? Um, from here, we actually have our actual learning lab. As you can see, we've got three different potentiometers. I'm not really sure what the 1M, the 100K, or the 10K is. Uh, it could be the amount of power that it allows through. Not really sure. We'll find out, right? So we got some other switches. This looks like a switch that can activate multiple different nodes at the same time. I'm not sure if they're even called nodes. We'll find out. We got other switches here that looks like on off. I'm not actually sure what to call it. We got a relay. Looks like it's got some sort of timer in here. We got a buzzer, speakers, a photoresistor, which this is the amount of light that comes through and actually helps generate power. Um, we got our milliamps. So I don't actually know if this is it does something. There's a nice glare right there. Um, we've got multiple different LEDs up here. Light emitting diodes. Sorry, let's be smart here. I'm not sure if you can see that. Um, and then we have an LED display. Right here is our breadboard. We've got 6 different compartments or columns. Up here is going to be our voltages, everything from 1.5 volts all the way up to 9 volts. And then down here is our ground. Looks like we have rows A through T, and if I'm not mistaken, I believe we can actually tie electronics across each of these columns, and each of the rows will be connected to each other as well. So with a row within a column, I do believe connects. I'm not sure if I'm saying this right. So let's put this aside. Um, all right, so here's our workbooks. We've got Basic Electronics Workbook 1. Um, this is what we're going to be following first. We've got, look at this, nice introduction, some fancy pictures. I'm assuming that these are uh, the symbols for schematics and things like that. Schematics, I think that's what electronics use, right? And let's see how many modules we've got. We've got 96 pages, and it looks like we have maybe 91 different. Let's just say we've got 80 different modules. So that seems fun. It's pretty good quality, actually. I expected it to be a little bit more destroyed coming from eBay and whatnot, but no big deal. Digital Logic projects. This is our Workbook 2. I'm assuming this is a little bit more advanced, something that I'm not ready for. Yeah, neat. I love the capitals. So if you're unaware, many years ago it was required for architects, electricians, people like that to write in capital letters. There was actually a whole script designed just for architects, just so the readability is there. It doesn't get you don't get confused. There's no it's very legible, right? Very engineer like, very structured. I think that's the word I'm looking for. Um, this here is going to be all the required pieces that we need. It looks like, let's see, we've got, looks like this is an earpiece. It's got some wires here, so we can go ahead and, um, what is it? So we can tie it into our circuits. Different wires. So I believe each of these wires are going to be different sizes, and in the instructions, they're going to declare what type of wire to use for whatever reasons. Over here, we've got our resistors, capacitors, and diodes, along with the LEDs. Let's see what this all does. It's kind of a hot mess, but no big deal. All right, hopefully these all still work. And then we got our chips. So I don't really know what chips do, except that they are comprised of everything that we're going to be doing in a much smaller scope. Neat. So I guess let's get started. I guess I'll talk about some other things too. I also picked up some tweezers, just because it'll help get through pulling the wires out. I don't have to break anything, right? So I'm going to move this box to the side. I've also picked up some additional wires that are of preset sizes, great for breadboards, and I I will have plenty of pieces at this point, so there's going to be no problems of running out. I'm not worried about that. I also picked up a box of electronic components, 2,000 pieces, everything from PCB boards, not going to be using that, to the resistors, capacitors, transistors, LEDs, everything that we need, if we didn't have this learning lab. But I got this just in the event that there was missing pieces, or there was any problems with the components in the box. So hopefully we don't need this. We're going to find out. To get started, though, we're going to need 6 AA batteries. They say that voltages doesn't really matter. I picked up some 1.2 volt battery AA's. They are rechargeable. Let's just make sure that everything's good. I checked these earlier, but batteries and things. I don't know. See? Nope, there we go. That works. That works. Yep. So if you're unaware, batteries do come in different voltages. Higher voltages release a larger amount of energy up front. However, they also burn out much faster. So the more energy they expend up front, the faster they drain. Makes sense, right? There's only so much power that you can put into a battery, and so a lower voltage battery will generate a longer lifespan versus a higher voltage being shorter. Let's go ahead and pull out our lab, sorry. And I don't know how to test this yet. this might all have to stop because if this learning lab doesn't work, then, well, I guess we're kind of screwed, right? And I'm not sure there's an easy way to determine that this works, being that we have to kind of make our own circuits to interact with this bad boy. So let's find out. Does it make a beep? Anything? No. No lights. Nothing. Well, isn't that just dandy? Let's go ahead and give you guys a better view here. Let's see. Do a narrow lens. What does this look like? Is this too close? No. I think this is going to be all right. All right, so let's get started with the book. I'm going to open up a worksheet. Let's see if this works. It worked earlier. Very nice. Move you over there. Fantastic. I need to interact with this bad boy. All right, so RadioShack's Electronics Learning Lab, Workbook 1, Basic Electronics, Transistors, and Integrated Circuits. So, in my limited knowledge, a circuit is basically just it is it is a how do I put this into words that I know how to understand? A circuit is a complete cycle, meaning it goes from a start to a finish and repeats. It's, I do believe, an endless loop of electricity providing a specific purpose. Um, I could be very wrong in this, so please let me know. Um, I also say a lot. I do apologize. All right, so introduction. We got the table of contents. Looks like we're going to go through. We're going to go up to page 19 originally and see what this gives us. I'm unsure, but I'm very excited. Um, if we want, we can go ahead and read each of these bits. For the purpose of this, how does this look? Is this legible-ish? All right, so I'm going to read from the book, but please follow along here. If you need, I can drop you a link to any of the PDFs. So, first bit is a note from the author. Congratulations, you're about to enter the exciting world of solid state electronics. The project in this manual will teach you many of the basic principles of electronics using circuits that are as much fun as they are educational. By the time you build the circuits in this workbook, you will be well on the way to designing your own electronic circuits. Neat. And you'll be well equipped to begin the digital logic workbook that is also provided with your electronics learning lab. And I love all of this capital letters. How to care for your electronics learning lab. One, always push the power switch to the off position down before building or modifying a circuit and when you're not learning or not using the learning lab. I would assume that this is because if you don't do that, you could short out the box. You could cause a pop, a hiss, a some sort of arc, some sort of whatever. Um, Not a big deal though, right? I say that. We'll find out. Um, Two, if a circuit fails to work properly when the power switch is pushed on, up. Actually, let's turn this off for a moment. Push the power switch off, down until you find and correct the problem. See page 18. Apparently, page 18 has some more information. We're not there yet. Excuse me. 3, overheated electronic. Let's see if I can do it this way. This might be silly. Um, 3, overheated electronic components often emit a distinct odor. Very important. If you notice an odor after switching the power switch on, push the switch off and check your wiring for possible errors. We've probably all experienced this before. That weird electronic smell, whether it's from your phone because it's super hot while it's charging or whatever it might be. I'm pretty sure most of us have smelt this smell. It's pretty unmistakable. Um, Never make a direct connection between any of the power supply points, V1 through V6, and ground. I don't know why. Neat. 5, the console LED's 7-segment readouts and potentiometers have built-in series resistors to limit, reduce current. When using loose LEDs, be sure to include a series resistor of a few hundred ohms, OHMS, or more. See page 48 for details. I think we'll find out what an ohm is shortly. The reason, so why this might be important is if an LED can only handle so much power before it burns out, right? And so what it's saying here is our LEDs have a set of its own resistors built in so that it doesn't burn out. I would imagine switching out the LEDs in this bad boy are not necessarily the easiest. I'm unsure though. The number 6, store loose parts provided with your learning lab in small boxes or plastic, in a plastic bag or container, as they can be damaged by static electricity. Static electricity. While building circuits, you can temporarily store parts you are using by inserting them into an unused portion of the breadboard. Just be sure that no components or wires from your circuits are plugged into any of the adjacent holes. Makes sense, right? If it's adjacent and we provided power, that means it's active. Also, doesn't seem like we were granted the safeness of that plastic for our components. So could be that we have some damage here. No big deal. Handling precautions for CMOS integrated circuits. The digital logic chips provided with your learning lab are of the CMOS family. The digital logic projects manual provided important information about the handling and use of these chips. Be sure to review this information to avoid damaging the CMOS chips. I don't know what CMOS is. You know what? I'm going to start taking notes on things that I don't know. Give me a moment. We got. Stand by. Sorry about that, friends. There was a slight interruption. No big deal. We got the ohms and we got CMOS terms. All right, let's get back to where we were. So that was 7, 8. Panel meter precautions. The analog panel meter is very delicate. Never connect it directly across any of the power supply outlets on your breadboard. Doing so may ruin the moving coil inside the meter or peg the needle so hard that it'll be bent. For this reason, you should never apply power to a circuit that uses the meter until you have carefully checked your wiring and corrected any errors. So this is our panel meter up here in the corner. I'm assuming. All right, batteries. Let's find out about the power of this bad boy. pull up what that means. Sorry. Uh-oh. Are we having some problems? Uh-oh. There we go. And we're back. Sorry about that. Okay. Let's go back to the internet. Batteries. Man, this thing goes quick. So, batteries. Your learning lab requires 6 AA cell batteries. Remove the battery cover on the bottom of the console and insert the batteries in the proper direction as indicated. The top row of the contact holes, V1 through 6, this area here, on the breadboard provides 6 different voltages from the battery. The voltages are 1.5 volts at V1, 3.0, 4.5, 6, 7.5, and 9 volts at V6. Um, in that order. These voltages are important to some of the projects, so be sure that the batteries are reasonably fresh while you're building the projects with your learning lab. Hence the rechargeable batteries. Kind of important, especially as we move forward. Um, the batteries will last up to several months if you remember to switch off the power switch on your learning lab off when it's not being used. So the reason why that's important is even though that a switch may be on, but not doing anything, it still is activated. It's still providing power, even though it's a much smaller one. So there is that draw because you have a positive and a negative connected. Um, Also, I'm talking out of my ass here. This could be incorrect. Fun. Be sure to remove the batteries if you plan on to store the console for an extended period of time. Fun fact: when I did get this, I did open it beforehand, but to check it out, the batteries inside the box were exploded, so they did not properly store this for us. Bummer. Um, so that could be a mark in the negative for us. This may mean that it doesn't work. I have no idea. It could have been a waste of $50, but at least we have a book, right? Frequently asked questions. Do I have to build the circuits in the order they are given? No, but if you're new to electronics or if this is your first lab kit, it's best to go through this workbook first. This will help you learn what you need to know to have the most fun with and to learn the most from your learning lab. There are many ways to build circuits. Do I have to follow checklists? If you are new to electronics, yes. With a little experience, you'll soon be building the circuits straight from the circuit diagrams. So it looks like we're going to be learning how to read some circuitry, some schematics. Maybe they're just diagrams, but I like the word schematic, right? Seems fun. Um, what do I do when it stand by? All right, and we're back. Is it okay? What do I do when a circuit does not work? Um, if you follow the instructions and use reasonable care, circuits should work the first time you push the power switch on. When a circuit does not work, Push the power switch off and change and turn to page 18 for some troubleshooting tips. So page 18 seems a little important. Um, I guess it's got some good information. Is it okay to modify or change the circuits in my learning lab manuals? Yes, even after you build a circuit, there will always be plenty of leftover parts for making changes, but you must follow basic electronic design guidelines before making such changes. Otherwise, you'll probably damage sensitive parts like ICS and transistors. I don't know what ICS is. So if you're new to electronics, wait until you've built most or even all of the projects in the manuals supplied with your learning lab before modifying your circuits. By then, you might even be able to design your own circuits. Should I be going through all of this? This seems like it might be you know what? Yes, we're going to go through this. Can I use the circuits in my learning lab in projects for school or at work? Generally, yes, but since the author and RadioShack have no control over what you do with your learning lab, we're not responsible for any adverse consequences. For example, you should never use your learning lab or its circuits for medical applications, safety devices, traffic controllers, or any other use that might somehow result in damage or property or injury to you or others. Neat. Wouldn't it be neat if came to the hospital and you saw a learning lab strapped to whatever device it was that was reading your heart? Oh, hey, look at this. The console electronic parts. Most electronic parts installed on the console are not easily installed on a solderless breadboard. Installing them on the console and connecting their LED to connection springs make them very easy to use. Compare your learning lab with the illustration below to become familiar with its many parts. All right, so we have the power switch, obviously. We've got the LED's display, which I guess is controlled by this bit. We have 10 LEDs. We have a transformer here. We have a meter. We got our photoresistor. We have a buzzer down here. We also have a speaker, this big box here. We have a relay. Neat. We got 4 push button switches, a breadboard, a DP-DT switch, battery compartment on the bottom, and 3 potentiometers of different potentials. So we can read a little bit more about what each of these bits do. The power switch applies power to the breadboard's power outlets, V1 through V6. LEDs display. The 7-segment LED display can produce the digits 0 through 9 plus special letters and characters. Each segment includes a series resistor to limit current so we don't burn it out. I don't know what a 7-segment LED display is. I hope they kind of explain it. We got a transformer. Many circuits cannot directly power a speaker, but they can be connected to a speaker through a transformer. Okay. Does it transform the electrical current? I don't know. We have our meter. The meter permits very tiny currents to be monitored. The meter can also measure voltage with the help of a resistor, I guess to make sure that we know shit's working. We got 3 potentiometers. Potentiometers are adjustable resistors. 3 different resistant values are installed on your console to provide the design flexibility. So I think one might be like larger changes, and then we got mid changes, and we got very minute changes. That'd be my guess. A DP-DT switch is a double pull, double throw switch is a pair of SPDT, single pull, double throw switches. Many uses including changing component values in a circuit. All right, that's what this bad boy is down here. Uh, so I guess this is double because it looks like, fuck, I don't know. We're gonna find out some fun stuff. We got the breadboard. This is where all of our fun stuff is really going to be happening. Um, we've got 4 push button switches. These will be used in many projects. Normally they are open, off. When they are pressed, they are closed. So I guess they might always be open until you press it, and then they're on. So maybe you have to hold it. Okay. Relay is a mechanical switch that is closed when current is sent through a wire coil. Though very ancient, relays still have many uses. This is what this bad boy is down here. The speaker transforms a fluctuating current into sound. It can produce a much wider range of audio frequencies than a piezoelectric device like the buzzer. Okay. Buzzer produces a loud tone at a frequency of about 1500 hertz. It includes its own built-in transistor oscillator. Okay, I don't necessarily know what that means. We're gonna find out though. Next page. You know, I didn't actually know I'd be reading this the entire time. Maybe I should have planned that a little bit better. All right, parts supplied with your electronics learning lab. Your electronics learning lab is supplied with a general assortment of components. Circuit symbols and generalized drawings of each kind of part are given below. Avoid misplacing these parts by storing them in the original packaging or in containers of your choice. Be sure to store the static sensitive parts, the power MOSFETs, and most integrated circuits in the original packaging, or in electrically conductive containers. Never store each part in a standard plastic bag or standard plastic trays or bags. Okay, unsure why? We'll find out. So we've got wires, right? So we've got a 30 centimeter wire, which is yellow. We have 20, which is blue. We have 10, which is 10. And we have 5 cm, which is white. All right, so I'm assuming that they're going to be calling out colors for us to use for connections. I probably won't be using these colors specifically because I would much prefer to use the multiple different ones that I have here. This seems like a much better option, right? Resistors. So I guess this is the sign for a resistor. Actually, I do know that because it's over here. Boom. Look at that. Does it have the terms that we wrote down earlier? No, it does not. All right. So resistors resist the flow of electricity. This makes them very useful for reducing currents to light emitting diodes, which can be damaged by too much current. Resistors are also used to divide a voltage into a smaller voltage. Resistors are used to increase the time required to charge capacitors and speed up the discharge of capacitors. They are also used to control the gain of amplifiers. Okay. Capacitors store an electrical charge. Makes sense. They capacitate. They hold capacity. Capacitors smooth a fluctuating symbol. They block continuous currents while passing current pulses. Capacitors in series with resistors are used in circuits that measure time or generate a series of pulses. They're often used with resistors. Ceramic discs and electrolytic types are the most common, with the latter having the most capacity. I don't know what that's a fun word. All right, we got a silicon diode. Cathode anode. Diodes are one-way valves for electrical current. Current flows one way but not the other. A diode is also a switch, since current will not flow until the voltage exceeds about 0.6 volt. The diodes provided with your learning lab are marked 1N4148. Since diodes are small, the marking may be in 2 or 3 rows of digits. Some diodes may have only the 4 digits 414 and a ring indicates the cathode lead. Ah, so that's the ring it's talking about right here. Okay. The Zener. Oh, next page. I want to build something, man. You know what I'm saying? All right. So we got the Zener diode. And standard diodes are both one-way valves for electrical current. Current flows one way, but not the other. But the Zener diode is connected backwards. It then blocks current until the voltage exceeds a certain level. The Zener diode provided with your learning lab turns on at 5 volts. It looks much like the standard diodes. A ring around one end indicates the cathode lead. I don't know what cathode lead is. Do you guys? Light emitting diode, LED. We should all be familiar with this, right? Most light emitting diodes, LEDs, emit light of one color. Your learning lab includes two loose LEDs, red and green. The cathode lead is indicated by a flat spot on the rim. Let's see if I can get an LED here. All right, do we see this here? Let's see. Not sure if we can see this effectively, but all right, so the flat end is here on the side with a shorter spike. The cathode lead is indicated by a flat spot on the rim at the base of each device. A row of 10 LEDs is installed in the console. LEDs most usually be connected to a resistor to reduce current to a safe value. The console LEDs are equipped with resistance for this purpose. Okay, so I don't know yet. I'm assuming one is positive and one is considered negative. And this flat spot should always be there to indicate which is what, so that in the event that we ever trim these for reasons, we continually know what that means. Sure. Sorry, I like to speculate while I go along. Bipolar transistors, PNP and NPN. Okay, bipolar transistors are like switches. Current flowing between the collector, C, I guess down here. Let's see if I can find one of these so we can pull it out. This bad boy is what I speculate. So we've got C, B, and E. Let me bust this bad boy out. So C, B, and E. Wow, we really can't see that very well. Doesn't help that we're delayed. All right, your learning lab, collector C and the emitter E on either side can be switched on or off by a current at the base, B. Transistors can also amplify by allowing a tiny fluctuating signal at the base to control a much larger current. Okay, your learning lab has two NPN and two PNP transistors. The part numbers for the transistors are usually printed on their front side. Various other numbers may also be present, but just look for the part numbers. I guess part numbers are super important. Let's see if I can see any of these. I'm pretty blind though. All right, I can see numbers. I wish I could show it here, but that doesn't really work out that way. And now we've got the power field effect. Let's roll down. All right, so we've got the power field effect transistors or MOSFETs. Okay. Metal oxide semiconductor, MOS, field effect transistors, FETs. All right, so that's what it means. Are the coolest of all the transistors. Please tell me more. So let me bust one of these out. Come on. So these are the coolest of all the transistors, I suppose. They make excellent switches for current flowing between the source, S. So we got G, D, S here from left to right. And drain, D, since they're very little resistance, when they have very little resistance when turned on by a voltage at the gate, G. This means that they can control much more current than bipolar transistors. They can also be used as amplifiers. Important, MOSFETs can be damaged by static electricity. Well, let's not be static, eh? So put that back. Now, integrated circuits. This is super important, right? Integrated circuits are what everything kind of all of our technology runs on. Everything from our phones to DVD players, computers, everything. Integrated circuits, ICS, are microscopic electronic circuits etched on a silver sliver of silicon called a chip and installed in a plastic, metal, or ceramic package with external LEDs or pins. Sorry, with external leads or pins. As shown here, one end of an IC integrated circuit has an index marker, usually a notch or a circle that indicates pin 1. Let's bust out one of these bad boys. All right. This must be, wait, usually a notch or, well, we've got a notch and a half circle, and then we got a circle here. It's kind of weird, right? I don't know what this means. I guess let's just go off that. That's what we're looking for here. This might just be a blemish from manufacturing. And by blemish, I mean it's purposely done. But hey, I don't know what I'm talking about. Oh, hey, more reading. Man, there's a lot here. Fun. All right, let's keep going, eh? The solderless breadboard. Electrical connections to the parts installed on your electronics learning lab is made possible by 69 spring terminals. So these are going to be the 69 spring terminals, I'm assuming, because this is where it terminates, so to speak. They're also springs, so I think it's self-explanatory, but I could also be wrong. Loose parts are installed on the solderless breadboard. The breadboard has 660 connection points. 30 of these connection points are provide 6 different voltages for your project. Okay, so now we're down to 630 usable ones, and probably just down to 600 because we've got the grounds here, right? You will insert connection wires and the leads and pins of electric components into the connection point. The breadboard is perfect for simplest projects using only a few parts, and it makes possible complicated projects that use integrated circuits. So it's a good way to prototype, or in this case, learn what we're actually doing. How the breadboard is organized. We've got the top row, which is the listed voltages applied to the 5 connection holes below, right? Insert positive plus power connection wires along this row. So this is where we're going to collect all of our power. The main section of the board has 600 connection points. This is where all of our magic happens. All 30 of these connections go to the ground, so that's everything down here, or more specifically here. Ground is important. I don't know why, but hey, I'm pretty sure there's lots of reasons. The lines through the connection points show how they electronically connected. Okay. Power is delivered to the solderless board only when the power switch is pushed on. Let's move a little bit further down, eh? And standby one. All right, sorry about that, friends. Let's get back to it. All right, how the breadboard coordinate system works. Each of the 600 connection points on the breadboard is identified by a coordinate system based on the row and column labels. Rows are indicated by letters and columns by numbers. Sure. The arrows below show the location of a connection point, G17. Boom. Okay. Let's see what that looks like here. We've got G 17. Boom. Yeah, that makes sense, right? Yes. Sorry, a few things are happening here. The projects in your learning lab will ask you to connect a wire to one or more of the 6 positive voltages along the top of the breadboard. You can use any of the 5 holes below the marked voltages. Makes sense. Some projects add more plus voltage connection points by running a wire down to a row on the main part of the board. Wait, let's do that again. Some projects add more plus voltage connection points by running a wire down to a row on the main part of the board. So I guess that's how we stack power. Sure. Use of any of the 30 connection points along the bottom of the board for ground. Sure. Makes sense. Next bit. To assemble circuits. Electrical connection to parts installed on your electronics learning lab is made possible by 69 spring terminals. Again, that's these bits. You will insert loose parts provided with your learning lab into the solderless breadboard. You will use connection wires to connect to the springs and to the parts you will install on the breadboard. Okay, that makes sense. Um, Inserting connection wires into the springs. So you pull back to insert a connection spring wire into a spring, bend the wire. Wow. Bend the spring sideways and insert the exposed metal portion of the wire into an open slot near the bottom of the spring. Okay. Be sure that the only bare metal enters the spring. Then allow the spring to return to its normal position. Be sure to keep the insulated portion of the wire outside of the spring. Remove connection wires by bending the spring away from it, then pull the wire. You can insert several wires into a spring terminal. For best results, insert wires on opposite sides of the terminal. Be sure to insert wires at different levels into the spring. Okay, um, different levels. Different directions that would I'm assuming to ensure that there is positive contact with the wire and the spring so that the connection can actually be made sufficiently. Um, all right. How to insert parts and wires into the breadboard. It seems like it should be pretty self-explanatory, but because we're doing this, let's do it. Insert a wire by connecting into a connection point by pushing until it stops. Sure. Do the same with parts having wire leads, parts with thick leads or pins, such as the transistors shown here, uh, require more force. Align the pins with the proper holes and then press down firmly on the part. Remove parts and wires carefully by pulling them straight up. Pry ICS up from one end and the other end. So try not to put your fingers on the electrical bits and pull from the long ways. Makes sense. Integrated circuits ICS must be installed across one of the 5 slots in the solderless breadboard. So that's a slot. These are slots. Interesting. Why? The ICS supplied with your learning lab have 2 parallel rows of pins. Each row should be inserted into the connection points along the opposite sides of the slot. Use care to avoid bending the pins. IC pins are sharp. Sure. Uh, Let me scroll. Install an IC by lining up the pins on one side with the correct connection holes, along with the edge of the slot. Rest the opposite side of the IC atop the proper holes on the opposite side of the slot and press down on top of the IC. Integrated circuit. If the IC is new, the pins will spread slightly and outward. Press the tip of the ballpoint pen next to the pin furthest away from you and push the pen downwards. Push the pen toward the row of connection holes while pulling it along the rows of pins. At the same time, press down on the IC. When the pen reaches the last pin, the IC should slip down into the connection point and rest flat against the breadboard. Okay. It looks good God, man. All right. Moving right along. More about assembly methods. Always push the power switch to off before you assemble a circuit. Be sure to install parts in the proper holes. A mistake might very well fry a component when you push the power switch on. If an incorrectly installed part survives, the circuit will probably not work properly. So this is where I guess frying comes from. That you apply too much power to it and it technically overheats and fries the components inside. Boom, it's no longer good. Makes sense. Uh, the two resistors are installed correctly. Be sure to keep the leads of parts from touching one another when they are installed on the solderless breadboard. Use these two resistors are inserted into the breadboard vertically. Their leads are separate from one another and do not touch. These two resistors are installed incorrectly. These two are installed improperly. The one on the left is pushed down, and the one of its leads is touching the lead of the adjacent resistor. The circuit they are installed in will not work properly if it works at all. Okay, I guess that's pretty straightforward, right? I'm going to do a sound check really quick. It's pretty straightforward, right? Yep, we're still good. What's right about this sample? What's right about this sample solderless breadboard circuit? The integrated circuit is straddling the slot. The resistors are vertical and not touching anything. All right, let's actually read this. The resistor is installed across the one of the slots in the breadboard, which means each LED goes to a separate connection row. Okay. This LED is installed across separate connection rows. One row goes to a resistor that limits current to the LED. The other row goes to an LED to a lead that goes to off the module to ground. Good. This integrated circuit is installed across one of the slots in the breadboard. This means each of its pins inserted into an independent connection row. Also, each of the pins on the IC enters a connection hole, and none are bent under the IC package. Correct. Okay. And more zooming, scrolling. What's wrong with the sample solderless breadboard circuit? Both leads of this LED are installed. Actually, let's take a peek. That's wrong. It's not going across the slots vertically, it's going horizontally, which means I'm assuming that these four teeth are going to get bent, and it's not going to work appropriately. Let's find out all of it. Leads of this LED are installed in the same connection row. The lead LED will not work. Okay. One end of the wire is connected to a row that goes nowhere. Okay. Both leads of this resistor are in the same connection row. The resistor will not work well. This integrated circuit is installed across one. Yep. Two pins on each side are bent under the IC. The IC must be installed with its long slide parallel. Okay, makes sense. I hope you're all learning. I am. It's a pretty dense read, eh? Electronic circuit symbols and diagrams. I'm assuming that this is woefully important for many reasons. Specifically, all of our diagrams are going to be containing this, or schematics, because I like the word schematic. Oh, hey, it actually says schematic here. All right, on pages 8 through 9, various symbols are shown alongside the components they represent. Those and additional circuit symbols are shown here. On page 14, we will use some of these symbols to represent a circuit that flashes an LED. Neat. Schematic or circuit diagram symbols. All right, so we've got connected wires, unconnected wires, push button switch, normally open. So open is off, see? And I'm assuming it's off because there's no connection here. It is open. The SPDT single pole double throw switch, which are pieces of the DPDT double pole double throw switch. Okay, sure. We've got positive voltage connection, so plus V. I wonder if it's also got that arrow. We've got the ground connection, which looks like a downwards arrow into, I don't know, some lines. Sure. Resistor looks like little mountains. Um, Potentiometer is a variable resistor, so it makes sense that it's a very similar symbol with a down arrow. Sure. Okay. I'm not sure Sure. Whatever. Don't matter. Um, Photoresistor light sensitive resistor. So again, we've got a resistor here wrapped in a circle, a line. And okay, I hope I would like to know where these symbols came from. Maybe we'll learn. Ceramic capacitor. We've got the electrolytic capacitor. We've got the diode, the Zener diode, the light emitting diode. We've got the NPN bipolar transistor. We've got the PNP bipolar transistor. Good Lord, man. Power MOSFET transistor. So that's the big three-prong one. We've got an integrated circuit. This is a 555. I think this is one of the most commonly known and utilized ICs. We've got the meter. Oh, wow, that's super self-explanatory. Uh, we have a relay. Interesting. Transformer. I guess because it's transforming. We have a magnetic speaker. We have the piezoelectric buzzer. I think that one's going to mess with my ears. Um, Various other symbols for integrated circuits and digital logic are introduced later. Cool. Sorry, 1 second. Sorry, trying to find my composure here. I promise we will get into some actual circuitry here soon. Um, it looks like it's this page, right? Yeah, fun. So, getting started, a pictorial view of a circuit that flashes an LED. The illustration below is a pictorial view of the circuit that uses a 555 integrated circuit to send pulses of current to a red light emitting diode. Pictorial views are very clear, but they are not practical for complicated circuits. Circuit diagrams in which electronic parts are represented by the symbols on the facing page are more commonly used. Makes sense because I guess reasons. Just because it's written in this book is how it is. Maybe other cultures don't read them the same way. You know what? That's speculation, and that is a terrible one. So uh, we've got the resistor R3 limits current to the LED, reduced to 470 ohms for brighter flashes. Okay, the LED near the lead near the LED flat spot must go to pin 3 of the 555. So, boom, here we go. That's the flat end. And then we've got the other end, which goes into the resistor. Or at least maybe this goes this way, right? So we've got the positive end of the power. It's going to come over this way, hits the resistor. It's going to hit the LED, which then is connected to the slot 3 of of the 555. I'm following. Um, the capacitor C1 controls timing and duration of flashes. So that's this bad boy. which that's the negative connected into slot 1, and then also to the negative side of the capacitor. The positive side capacitor is connected to slot 2 of the 555 and wraps around and hits slot 6, and it looks like this is another resistor of 10K. So resistors R1 and R2 control the timing and duration of flashes. Okay. Colored bands of resistors indicate their resistance. K means 1000, 1K is 1000 ohms, 4.7K is 47 ohms, 10K is 10,000 ohms. More about this later. Okay, now we're getting to places that get a little complicated. The circuit diagram below is equivalent to the pictorial view above. The same circuit is shown in both diagrams. The most important difference between the two drawings is that the circuit diagram, that in the circuit diagram, the pins of the 555 IC are not shown in the same arrangement they have on the actual IC. This shortcut provides a simpler way of representing the circuit. Note that the 6-volt battery is replaced by symbols. Okay. Compare the two circuits by checking to. Can we see this? Yes. Compare the circuits by checking to see if the same connections are made to each 5 pin. Start at pin 1. Pin 5 is not used. This is an excellent way to find mistakes when you build circuits on your Learning Lab's breadboard. The resistors are marked with a code of color bands. Yellow equals yellow, bio equals violet, BRN equals brown, ORG equals orange, BLK equals black. Later, we will cover how to interpret this code. All right. Fun. Now we're actually getting to the meaty stuff. This hasn't been meaty so far. I think this is all we need for this one. Please stop scrolling. Stop it. Only an hour and 30 minutes into the session, and we finally get to check this out. All right. Getting started. Build a simple LED flasher. Now you're ready to build the LED flasher circuit on page 14. Building this circuit will help you prepare to build all of the circuits described in your Learning Lab manuals. Tip: circuit building goes much faster if you first gather together all of the parts you will need. Also, be sure to remove unused parts from the breadboard. All right, so we are going to need a 555 circuit, which is this bad boy. So as you can see, these pins are bent, very nice. We have here what does this look like? Stand by. Oh, it's a little too close. So we've got 4 pins on one side, 4 pins on the other, total of 8 pins, easy peasy. Now I know it says to place it onto the board. I am actually just going to place it here. Not that you can see it. So I should move it. Boom. Again, that's bad practice. We are going to need 3 resistors. So because let's figure it out. Yellow, violet, red. Yellow, violet, red. Yellow. This is gross. So future plans will be to lay out each of the required pieces before we get started, so we're not trying to figure it out. Well, son of a... How about this? So what colors do I need? I need yellow, violet, red. Man, I need better light in here. You know what? Stand by while I find these pieces and we will figure it out. All right, so I got all the pieces here collected. Some of these have been used. Again, don't know if this is going to be a problem or not. Let's cover. So we got the 555 integrated circuit, right? Super easy, straightforward. 4 pins, and all that. I have 8 pins, 4 on each side. We've got our yellow, violet, red resistor right here. Can we see this color appropriately? Or is that going to be too difficult? Yeah. I don't know if I have a good way of getting this visualized. Might be too close. Nope, it's having problems. All right, so you can kind of make out the colors: yellow, violet, red ish. Um, we've got the brown, black, orange. Sorry, this is the brown, black, red. It's been used. It's kind of destroyed a bit. Um, you know what? We're going to pause this one more time, and I'm going to see if I can get some better light in here. Give me some moments, and we'll make this happen. All right, friends. I think we have some better lighting. Maybe not like the most ideal, but I don't know. We'll see how this goes. I'm unsure. Anyways, all right. So let's get back to where we were. Where were we? Let's begin right again. So we've got this lovely boy. This is our 555 chip. Uh, I'm assuming it is. It doesn't say 555 on here, but it's the only one that I think looks like a 5 by 5. Sure. Um, can we actually see this time? A little bit. Not really. The zoom on this bad boy is terrible. Terrible. We've got, again, brown, black, red. Always going away, uh, starting from the band. I don't know how to explain this. Anyways, so we got brown, black, red. This is the third one. This is our R3. Our R1 is the yellow, violet, red. Let me turn it the proper way so we can keep it all in the same way. So I'm not it's a bummer you can't really see it. I'll have to figure out a better way of doing this in the future. Um, and then we've got our brown, black, and orange. Right. Um, Next up, we've got our capacitor, which is a 10 UF, which is right here. Um, I don't know how to really describe this. On here, it shows a 10 UF 50V. I'm assuming that this is 50 volts. I wish that again I could show this, but it does not look like it does a thing for us. It's no big deal. We'll figure it out. Next up is a red LED, right? Pretty straightforward. We know what this is. However, I also grabbed the green LED only because I don't know if these LEDs actually work, right? Let's get started. So the circuit specifies a red LED for LED1. You can use a green LED if you prefer. Makes sense. Excuse me. This circuit is a basic astable or free running pulse generator. Neat. The pulse rate is determined primarily by the C1 and the resistors through which C1 charges in R1 and R2. The width of the pulses is controlled by R2. R3 limits the current through the LED to a safe value. Notice how all of the connections to the +6 volts are shown separately. This style is used in most of your learning lab diagrams. So I don't think this is going to require three different connections into the 6 volts. I think it's only going to require one connection that comes out, and it's going to feed our entire circuit. We'll see what that looks like here soon. So let's get to building the circuit. Step 1, push the power switch off. We are, boom. Insert the 555 IC across slot 3, pin 1 at F15. All right, so we got pin 1. So hold on before we get started. So previously we didn't have we had a circle and then we had a notch. In this one, we only have a circle, and it seems to be indicated right up here. It's kind of blurry, but either way, so that's our circle. So that's going to be R1. So we want R1 located at F15, right? So we've got F15. Boom, F, go down, we got 15. Makes sense? So we're there, and push. Don't push it too hard. Don't force it. If you're having trouble with it, no big deal. it is what it is, right? Um, pull it out, try again, try to reseed it if necessary. Um, so yeah, that's what we've got right now. So that's all set. Easy, easy peasy. Next up, connect I14 to F17, which is the white wire. So I'm not going to use white wires, but I will be using smaller wires. So we want I14 to F17. So we've got I14. You know what? That's too big. So we've got I14. Yeah, that's too small. Since I don't know what I'm doing, this is going to just take a little bit longer while we figure out format and stuff, right? So once again, I14. Boom. Right there. Which is at the same pin as slot 4 of your 555. And this goes to, what was it, F17? This goes to F17, which, hey, that's not good. We're going to need a bigger one. Why do we need a bigger one? Well, we need a bigger one because we want it to not necessarily be a super snug connection over that. So, boom, and boom. So that's what it looks like. I guess that makes sense. From here, we've got the G14. So now we're at step 4. Connect G14 to H17. G14 to H17. Let's grab another green. G14 to, what was it again? H17. Hello, friend. I'm not sure who's viewing, but welcome. I hope we're going to have some fun. All right, so on to step 5. Connect F20 to V4, which is a white wire. Again, F20 to V4. We got F20 to V4. All right, boom. I don't like that one. All right, so there's that. Step 6, connect F13 to ground, which is a red wire. The red wires are kind of long. Do we think this one will work? F13 to ground. We're just going to select any ground. No big deal, right? It's a little too far. Next, so that was again F13 to ground. Doesn't necessarily matter what ground. Ground is ground. Step 7. insert the R1 across G19 and V4. So R1. R1 is the 4.7K, which is the yellow, violet, red. Yellow, violet, red. And it says, again, so yellow, violet, red. We're going to drop it into, once again, oh, does it matter which way it goes? I don't fucking know. G19 to V4. G, here's 19. You know, up to G, which is the second slot. Boom. Sure, I guess. We are making, we're building a simple LED flasher. So it's going to use a small chip, which is here. It's a 555. We're going to be connecting, a 555 has 8 pins, 4 on either side. We're going to be connecting each of the pins, or each of them, into different slots. And then we're going to utilize a couple resistors to control a pulsing LED light. I guess that's maybe what this is lab one. Um, we just spent the last hour and a half reading the first 18 pages of this nope, we're only on page 15. So the first 12 pages were just kind of the instructions. So this is day one. I have no idea what we're doing. So now we want to place, so now we're at step 8. We want to place our R2, which is the resistor 2. It's a 10K. It's the brown, black, orange. Brown, black, orange. This motherfucker right here. Super easy. Into G20 and H20. G20, which is here, to H20. I hate how long these are. This is not doing well for my OCD. Makes it look ugly. See, now this is not a good thing. See, our wires are crossing. And if you remember from the early instructions, it says don't cross your wires. Kind of like how the Ghostbusters say, don't cross your streams. So now they're separated. Now we want to insert our R3 resistor, which is this last one, which is the brown, black, red, between D15 and our V4. So D15 is going to be here. Let's straighten you out a bit. I think I need some, maybe some tweezers or something to do this. Or look. D15. Slot. So to give you a recap, this is the RadioShack Electronics Learning Lab 28280, and basically it's a all-inclusive lab that's got everything from LEDs to potentiometers to photoresistors, a buzzer, speaker, some switches. Um, Most importantly, your breadboard. It's got a power supply inside, which is fed um, to this top row, which provides the power to whatever our project is. Different voltages from 1.5 all the way up to 9 volts. It contains 6 AA batteries. But yeah, so we're now on step 9. Can you guys see that diagram okay, or the instructions? So we got D15 into our V4. Doesn't necessarily matter where, I guess. Don't actually know if I'm doing this right. This is probably not going to work, but hey, that's what we're here for. And so that's step 9, which is the D15 into slot V4. Okay. Now we are going to put in our LED. insert LED 1 across D13, which is the anode, and H13, which is the cathode. So if we remember properly from previously, the cathode is the side with the flat end, or more specifically, a fresh LED is going to have a long wire and a short wire. Sorry, that's backwards. A long wire and a short wire cathode and a long wire. It's designated by this flat piece. So D13 to H13. The anode is in D13. Where are you? D and H. All right. And now for our capacitor, the last piece of our puzzle. This is step 11. We want to add the plus side. Shit, do we know what the plus side is? Let's go refer back to where capacitor plus side. Does it matter? It should matter. Oh, fuck. Oh, man. Get out of here, bro. I don't know you. G11 and F11. G11. G11 and F11. So I don't know if this is actually going to be inserted incorrectly. We're about to find out. No. Yay. Let's switch it around. Well, shit. I was afraid that this would happen. Let's try a different LED. Of course not. Son of a monkey. All right. I guess let's revisit our instructions from top to bottom. Power switch off. Done. We've got the 555 IC across slot 3. Pin 1 at F15, right? So we've got F all the way to 15. Yep. Indicated by this lovely circle down here. It is now straddling the slot. That is in appropriately. Great. Now we want to connect I14 to F17. So we've got I14 here connected to F17 here, which is specifically slot 4 and slot 5 of our 555 chip. That looks to be correct. Next up, we've got our G14 to H17. So we've got G14 here, which is slot 2, into our slot 7, which is, oh, is that G or is that H? No, that's correct. That is H17. Perfect. So that is correct. Next up, we've got F20 connected to V4. We've got F20 right here. Wait. Oh, no, it's this one. All right. F20, which is boom, into our V4. Nice and snug. Best connection we've got so far. Next up is our ground. So we've got F13 to ground. Boom, F13 is up here, as we can see, nice and easy. It goes here. Makes sense, right? All right, step 7. This is where we get into the resistors. This is where my problems could actually exist. Are any of them touching? No. Are they all connected? That one, maybe not. Maybe not that one either. Oops, that was my head. Okay. Okay. I hate these. Perfect. All right, so just to recap, we got R1. R1 is our yellow, violet, red, yellow, violet, red. That is designated G19 to V4. We are in G19 to V4. Boom. Makes sense. Next up, we've got the R2. The R2 is going to be the brown, black, and orange, which is right here. Brown, oh, that's brown, black, red. Brown, black, and orange is here. That is stated to be G20 to H20. So we're at G20 here to H20 here. Looks good. Next up, we're at the resistor 3, designated brown, black, red. This one's supposed to be D15 to RV4. So D15, yep, boom, makes sense. To RV4, nothing's crossing, everything looks good. Next, we got our LED across the D13A node. So D13 is here, right? It looks like it's correct. Let's double check what the cathode is supposed to be here. LED, not specified. LED, here we go. The flat spot, the cathode lead is indicated by the flat spot at the rim of the base. Okay, so we've got the cathode in the wrong fucking spot. Winning. Let's reverse you. So, to recap, this is supposed to be the A node. The A node is at D13, right? The cathode is at H13. All right. Last piece. Insert our C1 across G11 plus and F11 minus. So we've got G and we've got F. So, motherfucker, let's try switching you around again. This is neat. I love things not working. Would probably made sense to do this before I streamed it, but you know, YOLO. D13 to H13. You should work. Guys, are we having fun yet? I don't even know. I don't even know. And obviously, there's no indication that this machine is working, this box. So, son of a bitch. Let's try switching you again. Wait. Yeah. Why is there no light? How can I appropriately test that this box works, this lab? Um, hmm. Is this, you know what? My chip might be busted. Let's do this. We're gonna go into my box of fun toys. Because I was unsure if this was actually going to be a problem, and it looks like some of our components may be bad. I don't know. It could just be me. Also, highly possible I need a 10 UF. Isn't electronics fun, guys? Oh, hey. I found how negatives work in this. So F11 is the negative, which is where we were at. So let's get rid of you. Um, that's 100 UF. Give me a 10 UF, bro. Boom. Okay. And we are going to redo that bad. Friend in our channel, Mr. Sportco. Can you hear me okay? Is everything coming across all peach keen? Of course. So no dice here. What in the F? Alright, so next up is our chips. We're going to replace the chip with a brand new one because we've learned a few things. I think. I like to believe I learned a few things. I don't know if it actually indicates what a 555 is. So we need the NE555. Motherfucker. I can't even read this shit. Not you. Not you. Not you. Definitely not you. Nope. I'll find you. You're gonna be here. Ah, boom. NE555. All right, let's redo this. We're gonna pull you up, pull you up, pull you up. You know what? That's not even the correct chip. Today I've learned. So back to spot one goes to the F's. And drop it. Wait. So now we're recapping. Where are we at? We've got I-14, boom, to F-17, which is up here. Yep, easy peasy. And then we've got G14 to H17, which is there. Ah, look at that. We have some power. Neato. All right, so we learned a couple things in that. One, use the right chip, because the chip that I originally used was not the right one. I would show you it, but it's actually a 386D. I have no idea what that means, but it's obviously important because now things are working. All right, ain't that some shit? I'm gonna put these away just so keep my work area clean. All right. Well, hey, that makes me excited. Now we've got another piece that we can do. There is a some additional steps, which is to test the circuit, check the circuit for errors. We did that. When you're sure all the wires and components are installed correctly, push the power switch up, on, and the LED should begin flashing several times per second. Problem, go to page 16 and 18. Well, we were able to go back over all these steps, recheck our connections. We discovered that the chip in use was actually the incorrect chip, obviously. Well, not so obvious, obviously. Um, so yeah, and the next step is going further. This simple circuit is easy to modify to slow the flash rate to about once every 2 seconds. Insert a 100 UF capacitor across C1 at G12 and F12. So let's grab a 100 UF. All right, boom, nice and simple. Hello, friends. We are back. So, uh, the next bit we're going to be on is the build a 555 black box test circuit. Uh, a black box circuit is one that's there when you need it. You can use it even if you don't know how it works. This black box test circuit produces a tone with a frequency controlled by a resistor and a capacitor. It will help you understand how resistors and sorry, excuse me. It will help you understand how resistors and capacitors work and they're on their own and together. The parts you will need. So we need one 555 chip, easy. We need our R1 resistor one as a uh, brown, black, orange, same as our first go around. We then need our brown, black, red. And finally, we need our brown, black, brown. Great. We then move into our capacitor, which I believe this is actually considered a ceramic capacitor. Come on, buddy. Get in there. Which is designated F104. And that is it. It's pretty straightforward and simple. Nothing too fancy here. Let's see. Let's see where we can go. We're going to go to the circuit diagram. The numbered circles are springs on your console. The springs are borrowed from unused parts. Be sure that the DPD switch is pushed down. For test purposes, the circuit can be shown as a box with external connections like this. Okay, buddy. No idea what that is. Leave the circuit on the breadboard while you build the switch. Resistor and capacitor circuits on the following pages. Switch the tone off by removing the red wire at V4 until it is needed. Okay. Sure. No idea. Hello, comrade. How are you doing today? Thank you for joining. We're just doing some fun electronic bits. We are covering the Electronic Learning Lab 28-280 by RadioShack. It's a pretty solid setup. It cost me about $50. Goodbye. Bummer. All right, so let's get started. So power switch is off. Insert. Yep. So notch. Remember, notch or the circle indicates where slot 1 is for our chip, and we want this at F15. Much like the first time. I imagine that F15 might be a good neutral because it's directly center in the board. Of course, that didn't go in correctly. Boom. Beautiful. All right. So now we want to move I14 to F15. Sorry, I14 to F17. So here we go. I14 to F17. This is almost identical to, well, so far, this is exactly identical to what we were previously doing. Then we are going to go ahead and do G14 to H17. G14 here to H17, which is here. Right? Now, these wires can cross because it is where it's not actually touching bare wire. It's not going to cause us any sort of problems, hopefully, right? All right. So next up, we're going to connect F11 to ground. F11 to ground. Let's do So F11 to ground. Boom. Straightforward. Next up, we've got F20 to V4. So F20, boom, to V4. So, boom. Let's do a shorter one. My head was just in the way. Sorry about that. F20 to V4. If you're unaware, I really like straight lines and whatnot, and unfortunately, the wires it came with are far too long for a lot of these projects. At least I'm saying that. I have no idea. I just know there's 5 colors versus mine, which has like 15 colors of all different sizes, and I am enjoying. All right. So we are connected to ground. We're connected to power. Now we want to insert our R2 across G20 and H20. So R2 is the brown, black, red right here. So G20 to H20. G20 to standby one. Sorry about that. Now we are connecting spring 40 to ground. Spring 40, which is our DPD switch. Okay, to ground. It's not a super long connection. I think we can get by with this. I think this might be the longest I've ever talked in quite some time. Boom. All right, so slot 40 is now connected to ground. Feel like maybe I should zoom this in. Is the quality pretty poor? I can't tell. Let's validate sound again. Yep. All right, so step 8 is done. Step 9, connect spring 41 to G11. 41 to G11. Way the F up here. Oh, that yellow one's huge. Yeah, red man. No, not you though. 41. G11. So that's 41 to G11. Now we need 43 to I11. That's a long one. a little long here. It's fine, right? Excuse me. And now we want to do 44 to G17. So 44 is that G. What? Well, look at that. Already found a mistake. Boom. All right, let's do this again. Spring 44, G17. Too short. 44. Let's try sticking you in first. That's what it's easy. Okay. And we're there. Now 60, connect spring 68 to F15, 68 to F18, which is here. That's a long one. Not quite. Give me that blue. That's not, yes it is. All right, so we want to do 68 to F68 to F18. Oh, that wire is so fucking, it bothers me. Okay. Easy peasy. Now that's 68, right? Yep. So now step 13, connect spring 67 to H11. Wait, 67. Okay. 67 to H11. You see how this starts to get super messy? I believe we can do this better. Connect spring 52 to I20. So we've got 52. Really? That seems okay. 52 to I20. 52 to I20. To I. Good God, it becomes a mess. Okay. So now we want to insert R1. So that's our brown, black, orange. Boom. Brown, black, orange. And we want to do that between 43 and 44. 43 and 44. Okay. Next up, step 16, we want to do R3 which is our brown, black, brown across 67 and 69. So we've got 67 and 69. Fantastic. And now we're going to insert, is there 66 on here? Apparently not. And next up, we're going to do C1 across 40 and 41. All right. Apparently, this is supposed to work. Uh-oh. Well, shoot. Okay. Once again, it's not working. So what is our problem? Where does that exist? Standby one. Fucking internet, man. All right. So we have a problem. And as we have learned, we need to go through each of these steps and figure out what's wrong. Yay! All right, so one by one, power switch off. Insert the 555 IC across slot 3, pin 1 at F15. Boom, that is F15. Bingo, bango, bongo. All right, step 3, we need to do I14 to F17. So we've got I14 to F17. Next, we've got G14 to H17. Yep. Now we've got F11. Where are you at, bro? F11 here to ground. Bingo. Oh, no. No, sir. That is not ground. That is ground. And there it is. Okay. So what all are we supposed to see? I'm not sure. check the circuit for errors when you're sure everything is installed correctly. Excuse me. You know what? We probably should have gone over these steps one more time before we tried turning it on, because obviously there was an error. It was easily caught. All right. Um, resistor test. Remove R1, the tone will stop. Now replace R1 with a 100K resistor. The brown, black, yellow. Let's get a brown, black, yellow over here. Brown. Brown, black, yellow. Boom. Okay. So R1 was the one that we placed at step 15, which is 43 and 44. So I'm going to take you out. I'm going to put you in. Now, what does this do to us? I suspect that the tone is going to be deeper because I assume that we're resisting more of the power. I don't know. Yeah. Wait, did I say higher or lower? I think I said higher, which means I'm wrong. So it's now more bassy. Because we're limiting the amount of power, therefore it is a deeper tone. Okay. uh, leave the new R1 in place and try the capacitor test. Okay. Remove C1. Which is our 104 capacitor. And let's do a 103 capacitor. I think that might be smaller. Okay. So we are replacing this bad boy. All right. So as we can tell, the pitch is higher, but also not as loud. I don't know if that's the point, but hey, well, it was supposed to be higher frequency, yes. All right, so that was the capacitor test. Um, so I guess that's done with this lab. I guess now we move into some other things. Well, shit. Okay. Well,
We just did roughly 2.5 hours. Um, I'm not sure what I want to do now. Should I keep going? Should I stop? I think I might do I think I might pause it. Yeah. Hey guys. Well, thanks for joining. If you enjoyed, please follow. If not, it is what it is. It's been fun. Yeah. Have a great day, all.